In the early 20th century, humanity had to hit the cosmic reset button. Our understanding of the universe wasn't just outdated, it was flat out wrong. Back then, we thought the universe was static, unchanging, and limited to just the Milky Way. Well, surprise. It turns out the cosmos is much more dynamic and way bigger than we ever imagined. And who's responsible for shattering this celestial illusion? You guessed it, Albert Einstein and his groundbreaking theories of relativity. In 1915, Einstein introduced his general theory of relativity, flipping the script on how we perceive gravity. Instead of being a mysterious, invisible force acting instantaneously between two massive objects, Newton's take, gravity became something much cooler, the curvature of space-time itself. Matter tells space-time how to bend, and bent space-time in turn tells matter how to move. Elegant, right? Einstein didn't stop there. That same year, he developed the Einstein field equations, a set of formulas that form the backbone of general relativity. These equations work like a cosmic Swiss Army knife, capable of describing how mass and energy shape the universe. When applied to regions with relatively low mass and energy, they lead to Minkowski space, a flat, four-dimensional spacetime that aligns with special relativity. Here's the thing about Einstein's field equations. They're not a one-size-fits-all solution. Instead, they're more like a universal toolkit, capable of yielding different answers depending on how you use them. Take Carl Schwarzschild, for example. By solving these equations for a point mass, he discovered something extraordinary. The very concept of non-rotating black holes, the cosmic enigmas we now know and, cautiously, admire. But here's where things get even more mind-bending. The idea that space-time itself can evolve over time depending on what's inside it has been around as long as general relativity. That's right. This isn't a new revelation. It's a direct consequence of Einstein's equations. Yet despite its elegant logic, the notion of an expanding universe was a tough pill to swallow. And let's be honest, the idea still leaves many of us scratching our heads. Think about it. If the universe is expanding, shouldn't everything inside it, including us, be expanding too? Are we secretly growing along with the cosmos without even realizing it? It's a mind-blowing thought, isn't it? Well, let's untangle these questions by diving into how the universe actually expands. How does the universe expand, and how do we know? Let's rewind to the 1910s, a time when the mysteries of the cosmos were just beginning to unfold. Enter astronomer Vesto Slipher, armed with a cutting-edge tool of the time, spectroscopy. Slipher used this technique to break down light from astronomical sources into its component wavelengths. Here's the fascinating part. Whether you analyze light in a lab or from our sun, certain atoms always emit and absorb light at the same wavelengths. Why? Because these wavelengths correspond to the quantum transitions of electrons in those atoms. Imagine looking at a hydrogen atom's emission spectrum. It's like a fingerprint, unique to hydrogen and impossible to mistake for anything else. The top band shows visible light, and the bottom one is hydrogen's emission spectrum, complete with distinct spectral lines. But here's where things get cosmic. When Slipher applied spectroscopy to light from spiral or elliptical galaxies, he noticed something unexpected. The spectral lines were still there, but they were shifted, either stretched toward longer wavelengths, redshift, or compressed to shorter ones, blue shift. This was the now famous redshift and blue shift phenomenon. So, what does this have to do with the universe expanding? Picture the sky filled with nebulas, those glowing clouds of gas and dust. The larger and brighter ones, which are closer to us, appear more bluish. On the flip side, the fainter and smaller nebulas, which are farther away, take on a reddish hue. This color shift is a clue, a cosmic breadcrumb trail that reveals the universe isn't static, but expanding. Why was this happening? The answer came in 1923, when Edwin Hubble made a groundbreaking observation. While studying faint flashes of light in the Andromeda Nebula, he realized something astonishing. At first, these flickers were thought to be novas, stellar explosions. But no, they weren't novas at all. They were variable stars, and thanks to Henrietta Leavitt's pioneering work, we could use them to measure cosmic distances. Remember how we started this journey thinking the universe was static and limited to just the Milky Way? Well, Leavitt and Hubble's discoveries shattered that illusion. They revealed that our galaxy wasn't the entire universe. It was just one player in a vast cosmic symphony. Hubble, with the help of his assistant Milton Humason, kept measuring the distances to various nebulas. Meanwhile, other scientists were connecting the dots. In 1927, Belgian physicist Georges Lemaitre concluded that the universe was expanding. A year later, American scientist Howard Robertson independently reached the same conclusion. But it wasn't until 1929, through Hubble's extensive studies, that we had definitive evidence. The universe was indeed expanding. So, does everything expand along with the universe? By now we're on the same page. The universe is expanding. But here's the million-dollar question. Does everything inside it expand too? And if everything is expanding, why aren't our atoms drifting apart into chaos? The answer is surprisingly simple. Not everything expands with the universe. To illustrate this, let's consider galaxy clusters, which are bound together by gravity. A prime example is the Virgo cluster, located about 55 to 60 million light-years away. Based on the expanding universe model and its distance from us, we'd expect the galaxies in this cluster to recede at roughly 1,200 kilometers per second. But here's the twist. That's not what we observe. The Virgo cluster, situated in the Virgo constellation, is a massive gathering of galaxies, forming the core of the larger Virgo supercluster, which also houses our local group, including the Milky Way. It boasts around 1,300 to possibly 2,000 member galaxies. Here's where it gets interesting. While most galaxies in the Virgo cluster are indeed moving away from us, a few are blue-shifted, meaning they're actually moving closer. The speeds of these galaxies range from 0 to 1,000 kilometers per second, much lower than expected for an expanding universe. Why? It's because these galaxies are gravitationally bound to one another. Like bees buzzing around a hive, they orbit and interact within the cluster, resisting the cosmic pull of the expanding universe. Who truly experiences the universe's expansion? We've seen how galaxies in the Virgo cluster don't play by the universe's expansion rules. Why? Because they're part of a gravitationally bound system, which acts like a cosmic safety net against the universe's stretching tendencies. But this isn't just unique to Virgo. Similar patterns apply to many systems in the cosmos. For example, the distance between the Earth and the Sun doesn't increase as the universe expands. Why not? Because the Earth and the Sun are gravitationally locked in a stellar dance. The same goes for other celestial objects within our solar system. So, what stays unaffected by the universe's grand expansion? Let's break it down. Atoms and molecules. The distances between atoms don't expand because electromagnetic forces tightly bind them together. Humans. Surprise. You're also a bunch of atoms bound by electromagnetic forces, so you're safe from cosmic stretching. Gravitational systems. The distances between celestial objects bound by gravity, like stars within the Milky Way or galaxies within the local group, remain constant. In short, expansion is only noticeable in systems that aren't held together by gravity or electromagnetic forces. Anything bound by these forces stands its ground, while the unbound parts of the universe drift further apart. The expansion of the universe might sound like a mind-boggling phenomenon, but the familiar structures we know, atoms, humans, planets, stars, galaxies, and even galaxy groups or clusters, do not expand along with it. This is because these structures are held together by strong forces. Electromagnetic forces bind atoms, while gravity keeps stars and galaxies in place. What actually expands is the space between unbound systems. In other words, the universe's expansion is only noticeable in the increasing distances between galaxies, galaxy groups, or clusters that are not gravitationally connected. As physicist Richard Price humorously puts it, your waistline might be expanding, but you can't blame that on the universe. Thanks for watching.